tester, you know, we're physicists, we test everything. Ready, set. The Xenon Dark Matter project was born here in Nevis Labs with the first prototype Xenon 10 in 2002, and the collaboration started with a few groups, mostly in the US, and which has grown to include today more than 100 people distributed around the US and Europe and Israel. Xenon is one of the experiments which are looking for dark matter. And what is this dark matter? We know, and we know it quite precisely, and since a long time, that we live in a universe of which 95% is unknown to us.
The first steps of the project were taken in USA at Nevis Lab, a research facility operated by Columbia University. It was here where Eleonora Sasso and her team first started working on the idea of using xenon to detect dark matter.
Dark matter and dark energy are two of the most outstanding questions in physics today that we aim at resolving. And Xenon is one of the many experiments which are after the question of dark matter, what it is and how we find it.
We know dark matter exists. We have evidence for it at all times, from 3 minutes after the Big Bang to today. We have evidence for it at all scales, from the universe as a whole to just our Milky Way. The question is not, does dark matter exist? The question is, what is dark matter made out of? We try to answer exactly that question with the XENON project. We do that here in Italy in the Gran Sasso mountain range. There's a laboratory behind me, the Laboratorio Nazionale del Gran Sasso, which offers us one of the prime locations in the world to do this kind of research.
The Xenon 1-ton experiment is located in Hall B of the underground laboratory.
We are searching for events that are very rare, dark matter events. So we have to filter out all those events that happen very often. Those events come from cosmic radiation. To filter out cosmic radiation, we hide our experiment behind a kilometer of rock.
The Xenon experiment, like others in the field, is based on the hypothesis that the dark matter particle will, although rarely, interact with standard matter. And we are looking for the signature of these interactions, which are very rare, with detectors which are very, very quiet, very low noise detector placed very deep, let's say underground or under a deep mine.
Dark matter is one of the most exciting unsolved problems in physics. We know from indirect evidences that the universe is composed mostly of other forms of matter than we know. What we know, the atoms that we have here and all the molecules that we know and everything we have seen with telescopes, makes about 4 to 5% of the whole universe. And we know indirectly there must be much more out there in a form which we have never seen before. We have indirect evidences of what this kind of matter could be, and this is so-called dark matter and dark energy. And the dark matter is most likely composed of particles which are extremely inert and don't interact with anything else. And we actually know such particles on Earth, so-called neutrinos. They're emitted by the sun, by nuclear reactors and other sources. And we have found in the last decades ways to detect these neutrinos. So looking for dark matter is very much related to this kind of physics. So we know the technology how to hunt this kind of extremely minute interacting particles. So that's why in the last years a number of detectors have been built to try to hunt down, to directly detect these dark matter particles. We actually expect that the wind of wind particles flowing towards us, to Earth, through us and all the way to the Earth, and we're trying to catch some of these particles by scattering events inside our detector. A nice image is if you drive in winter at night and it's snowing and your light is on, you see all the snow coming down, and because you're driving, all the snowflakes come towards you. In the same sense, the Earth is moving through the cosmos, and these wind particles actually are coming flying against us like a winds of particles. That's why we call this also WIMP wind. And the difference to snowflakes is that snowflakes do interact, they stick to our windscreen, while these wind particles are so minute, they just go through the Earth, they go through everything, etc. There's millions of these particles coming through you and me every second, and the artist wants to catch one of them.
Construction began in July 2013.
Well, because we are looking for dark matter, we know it's actually there. It's not some weird property of space that we cannot explain. It's actually really responsible for the structure formation in the universe. It's responsible for the galaxy formation, for the formation of our own Milky Way. We have many, many independent pieces of evidence from cosmological, astronomical observation that dark matter is out there. We believe it's made of new particles. We know that stars, for instance, are made of the same type of particles that we have here on Earth, the same type of atoms. You know, we call this baryonic matter. However, the dark matter, we know it must be something else. There's no known particle that has all the properties that we are looking for. So the properties of this dark matter particle, among other things, is that it interacts only very weakly with normal matter, with the matter that we know exists. And because of that, it's very hard to detect. So with about 100 kilograms of liquid xenon, we just cannot find the dark matter. We don't have enough what we call target material, because of this interaction cross-section, as we call it in physics, is very low.
With 100 kilograms of liquid xenon, Xenon 100 is the second phase of the project.
Matter would never do that.
We are building the next phase of the project, the Xenon 1 ton, that will have more than 3 tons of liquid xenon in total, and then we define, based on the position of each interaction, our detector, we define an inner central region of about 1 or maybe more tons of liquid xenon that we use for the actual dark matter search. So the search goes as follows. We look for collisions between the dark matter particles and xenon nuclei, and there is some light in the UV region that is being produced, some free charge, and we are trying to detect these very, very small signals.
It was therefore necessary to make some modifications from planning the latest phase of the Xenon project. So what are the main differences between Xenon 100 and Xenon 1 ton?
The basic principle is identical. It's a two-phase TPC. So the only difference is bigger. Xenon 1 ton is much bigger. But the interaction, the events, the signal is the same. So you have a primary signal, a secondary signal. Secondary signal is always you drift electron, go to the gas phase, and then you produce S2. All these are the same. So the difference basically is the size, photosensor, and with Xenon 1 ton we use much larger, 3-inch tube. In terms of the overall experiment, it's different because in Xenon 100 we use passive shielding. Passive meaning you put a shield there, you don't look at them, but they just act as a shield, but you don't know. But in terms of Xenon 1 ton, we use a big water tank. So you just mentioned a PMT installed in the water tank. So you actually look at the veto, look at the shielding. So it's not a passive anymore, it's an active shielding. Because you actually look at it. If you have signal there, you can tell the TPC, no, there's signal here, you have to veto the event. So I think that's the main difference of the two experiments.
Often ideas can come from chance encounters, just like the one between Elena and Laura in 2001.
Elena, do you remember when we met the first time?
It's the beginning of Xenon, actually, the year I met you.
Yeah, it was
2001.
In Snowmass.
That was Colorado, right?
Right. And I was there actually talking about another experiment, about
I suppose
cryogenic dark matter search.
You were with the CDMS experiment.
Right.
Yeah, and I got interested in listening to what was the status of that field, the dark matter, and that's the year I decided to propose the xenon experiment to the NSF, right?
Right.
In that
yeah,
September.
you were the expert on xenon, working in gamma ray astronomy. No?
Gamma ray astrophysics, that's right.
Once I joined the collaboration, I had the honor and also the duty of sharing the coordination of the cryostat working group, or the TPC working group. And recently I also start to chair the working group, the speaker board, where we decide the conferences and the speaker for the conferences presenting the XENON results.
We need people that have experience in building a TPC, to purify the xenon that we use, to make suppressed backgrounds, to build all these components together. And that's in some sense like a soccer team. You know, you have 11 positions, and you find for every position the best player. Of course, then the team has individuals. All of them want to score, they are egos and want to play. At the end, the best team is where the team really works together. And that's, I think, the task in the collaboration, to adjust the growth of this collaboration, the team members, and to organize everything such that this works in a most efficient way, in the end, to win the game. That's what we want to do. We want to discover this dark matter.
The University of Bologna is part of the group involved in the Muon Vito project.
We'll detect muons, cosmic muons, coming from outside, penetrating the rock. So normally they are also even high energy muons. And going through the water, they will produce some light, and the light will be detected from the photomultipliers. That allows us to say, hey, a muon was there, and if we have at the same time a signal in the TPC, in the time projection chamber, we know that unfortunately it is not the dark matter, but simply the production of some signal from these muons.
Here on my computer we can see a picture of the full experiments with the service buildings, where we have on the last floor the cryogenic system that is a source of cold. In the middle floor we will have the DIQ of the experiment, so all the electronics capable to record the events, and on the last floor is the so-called restox, that is a container of liquid xenon when we are not using the xenon for the experiments. And close by on the side of the buildings we will see the water tank, and into the water tank we see installed the cryostat that is supported by a so-called stand, that is something a bit more complicated than only a stand, because it's also capable to make the cryostat horizontal with a precision of 0.1 millimeters.
My institute, or my group, is responsible for essentially two things. One is a mechanical engineering part. We're involved with, we're actually designing and building the support structure for the cryostat of Xenon 1 ton, which is supposed to hold the cryostat in the middle of this big water tank. And the cryostat itself is quite heavy, sort of 4 or 5 tons in weight. But the liquid level inside has to be controlled to a very fine degree, to better than 100 micrometers. So that's sort of a challenging from a technical standpoint.
The cryogenic system is composed of a cryogenic line and a cryostat that consists of 2 vessels, the outer one and the inner one, which actually contains the sensitive part. The insulation between inner and outer shells required to keep the cryogenic temperature is maintained all across the system. This is how we define cryogenic containment.
The use of the cryogenic system in an experiment like the Xenon 1 ton experiment is to maintain the liquid xenon target at a stable and precise temperature. And this we do with pulse tube refrigerators in our case. The other use of the cryogenic system is also with the heat exchangers to allow the fast and efficient circulation of the xenon from the detector volume to the purification system and back. The pulse tube refrigerators are, as the name says, are refrigerators, and they are used to extract the heat from the xenon gas, condense it, and return it as liquid into the cryostat. So the heat that comes from outside will transfer a bit of heat to the xenon and then make it boil, and this produces gas, and then the PTR are recondensing this gas, and the gas goes back as liquid. After it's condensed, it's liquid and goes back to the detector. So the goal of the cryogenic system, like I said, is to maintain the target at a fixed temperature, the liquid xenon target at a fixed temperature. And it does this by continuously recondensing gas that evaporates from the cryostat. A system like this, the features that you would like to have, like I said, is precise temperature control, because we want to maintain the xenon at a fixed temperature. We don't want it to vary in time. The other thing that we want is stable and continuous operation for long periods. Okay, so that means the equipment that we use has to be resilient, and it has to withstand sometimes unforeseen power failures or unforeseen equipment failures. And we want to maintain the detector with the liquid inside it for very long periods of time to take the data, let's say, over 3 years. So the system has to also have this resilience to potential equipment failures and stability. And this we do with having redundancy in many pieces of equipment. For example, redundancy in the refrigerators. We have 2 sets of refrigerator systems, right? Pulse tube refrigerators. And additionally, we also have what we call a backup liquid nitrogen cooling system. So the pulse tube refrigerators, there's a series of pieces of equipment that are needed to operate them. And you need electric power to use them. But if you lose electric power, you still want to be able to maintain the xenon in a stable state at the liquid temperature. And this we do with this additional cooling system, which is just based on nitrogen. The only thing you need is liquid nitrogen and a very tiny bit of electrical power.
A time projection chamber installed in the cryostat is the heart of the Xenon 1-ton detector.
TPC is the central part, also means it's closest to the dark matter target. That means it has to be very radio pure. So we made a big effort to select very clean materials for the TPC. And what you see here is basically only copper and Teflon. Copper is electroformed. It's one of the cleanest materials that you can get, simply because individual atoms build up the new metal. This is oxygen-free, high conductivity copper, very clean material, and we selected it specifically for our purpose. So we measured the intrinsic radioactivity of each component. And the same with the Teflon. Teflon is an insulator, because we will apply minus 100 kilovolt on the bottom here, maybe also only minus 50, it does not really matter, but that's the ballpark that we speak of. We will have ground up here, there's 1 meter in between, so there's a big electric field. So the copper rings will be on high voltage. The Teflon structure as an insulator in between will separate the pieces on high voltage to make sure that there is no shortcut. The Teflon serves a second purpose. It's not only a good insulator, it's also a very good reflector for xenon ultraviolet scintillation light. The TPC is the central part, so there are many institutions involved in the TPC. So the design was mainly made by Zurich, Bern, and Columbia, with people working on different aspects. Now this central TPC is mainly built by Zurich, so the construction. The bottom and the top array was designed mainly by Los Angeles, will be assembled in Heidelberg together with the people from Los Angeles. The structure on the top, the bell, the level, is currently made in Italy, according to a design mainly by Columbia. The high voltage system, again, was designed by UCLA, and basically the overall structure to make sure that everything fits together is in the hands of Bern and Zurich. We have the drawing that accommodates everything and make sure that it fits.
The cryostat actually is, let me say, the container of the sensitive device and of the sensitive medium that is the liquid xenon. And that means that at room temperature it tends to boil off. So xenon is liquid at roughly minus 100 degrees Celsius. So if you want to keep it in liquid form, you must contain in a vessel that insulates well this volume from the environment.
it could even be okay to use one of the other ones.
XENON 1 Ton is the collaboration between 21 institutions from all over the world. But how is the work divided between everyone? Who does what?
We are right now in the Faraday laboratory at the Max Planck Institute in Heidelberg. And what we do here is to make the test of all the photomultipliers that are going to be built into XENON 1 Ton. First of all, they go to Gran Sasso. They are then screened into these germanium detectors that we have, high sensitive, and then they come back here. And once they are here, we perform, first of all, test at room temperature, where we just characterize how well they perform, how is the amplification, how is the noise, and so on. And once we see, okay, the PMTs are fine, in the next step we mount them into a setup that we have dedicated to cool them down. We plug it into the photosensor and we mount the PMTs into the Faraday.
Our group is working in neutrino physics and neutrino mass since many years. And the main motivation of neutrino masses is that neutrinos are a part of dark matter. There's evidence that neutrinos are not the real dark matter, something else. And that's our big motivation to have joined the XENON 100 and now XENON 1 Ton experiment to find the particles of dark matter, the so-called WIMPs. That's our main motivation to join the experiment. And from our neutrino experiments, we bring back with us a lot of expertise in extremely clean materials. And so our responsibility within the XENON 1 Ton experiment is to clean the xenon, which is our dark matter target. And one part is, and for that we built a huge distillation column. That is just a prototype. The final column will be nearly 2 times higher. We purify the xenon from krypton. Why krypton? Krypton is another noble gas, similar to xenon, but krypton has a radioactive isotope, which is produced by mankind by nuclear power and nuclear weapons. And that is a little bit in our air, such little that nobody cares, but our super sensitive dark matter experiment XENON cares about.
The reason why you need more than one way to detect dark matter is that it's a very complex problem, and so you probably need different ways to look for it to really nail what the dark matter particle or particles are. And the advantage of direct detection is that it provides, if there is a signal, it's a pretty clear signal. There's no real other way to explain it if you see it. In the indirect detection, which is looking for sources in the cosmos, you have many other sources of gamma rays, for example, which could look like dark matter. And so even if you see a signal, it's hard to really nail it as dark matter, which is the nice thing about direct detection.
We extract xenon from the atmosphere, and naturally it contains trace amounts of other gases, in particular krypton in our case. And the presence of krypton in xenon for a search for dark matter, it's an issue because krypton itself is okay, but it has one radioactive isotope, the krypton-85. And the radioactivity of krypton-85 is such that if it is present at a very high concentration, we're going to have a very high count rate in the detector, very high noise, and therefore we need to reduce the presence of krypton in xenon to unprecedented low level, 2 parts per trillion. Usually when we get xenon from the commercial providers or suppliers, we get xenon which has parts per million concentration of krypton in it, and we cannot do a dark matter search which is sensitive enough with such high concentration. We need to reduce it by at least a factor of 1,000, so we are talking about parts per trillion krypton in xenon. Now we have learned in the meantime how to do this separation of krypton from xenon. We are using cryogenic distillation. It's a well-known technology, and we know it works very well, and we expect that we can reduce this concentration of krypton in xenon to this very low level. The question comes, how can we measure that we have achieved such a low concentration? And that's where the atom trap comes along. We were missing at the time that I made this proposal to the National Science Foundation, we were missing a very reliable and rapid tool to measure the concentration of krypton in xenon, and that is a very important tool that we need, especially as we push the sensitivity of these dark matter experiments with very large-scale detectors, such as the thousands of kilograms of xenon which will be used in the Xenon 1 ton.
Many institutions are involved in purifying the components used to build Xenon 1 ton.
In this laboratory we have these very nice devices from previous experiments, proportional counters, which have a very, very low background, and we can use them to detect few, maybe 5 or 10 radioactive atoms. So from any sample which goes to the experiment, the sample will come first here to the laboratory, like for example a cable like this, which is used to read out a signal from photomultiplier tubes. The cable itself may contain traces of the radioactive isotope radium, which then creates the so-called radon, radioactive noble gas, which diffuses out of the cable and would create a background in the experiment. We can also put this cable in a vessel here and trap this diffused radon atoms and transfer it to this device, to these proportional counters. And these traps are here behind me. You see this device with all the traps here, where we can trap disturbing gases like humidity, CO2, oxygen. The nice thing is this is a device fully made of quartz. It's built in our laboratory here, so in our glassblowers workshop. It's a unique facility here, and there are maybe 2 places in the world where such devices can be built. One is here, and the ultra-low background of this device is really the key, which enables us to push down the detection limit to only a few atoms.
Welcome to the Dark Matter Lab at Purdue University. We are standing in front of the xenon gas system, the system that is there to deal with the xenon gas, handle it, get it in of the detector, out of the detector, and work with it. Looks quite orderly from this side, but if we go to the other side, then we can see what is really going on. What we have is 2 stainless steel cylinders to store the xenon, because it's very expensive, we don't want to lose it. There's a flow controller. There's a relatively large gas system. The main part is the pump. You can hear that running. And this gray box down here, which is a getter. Basically, when you pump in a noble gas through a getter, it takes out anything that is dirty. Any impurities that you have in the xenon are taken out by the getter.
Xenon is not actually the only target that we could use in this detector. There are other choices possible, always using noble elements. So, for example, there are other experiments, also here, Gran Sasso, for instance, the Dark Side program, they use argon, liquid argon. But in our view, xenon is the best choice because it is a very dense material. It's about 3 times the density of water. And the dark matter particles, as we think they interact with the ordinary matter, they need mass, they need density. So the denser the material, the better. Then the nucleus of the xenon is quite large because the atomic mass is about 130, which means that the target for the interaction of dark matter particles is bigger. And also the scintillation light, which is the signal that we collect in the detector to look for dark matter, is quite strong and also easily detectable with standard photomultipliers.
So liquid xenon, as you know, is a scintillator, and when particles interact with it, it emits light and charge. Different types of particles create a different response in the xenon, depending on how much energy they deposit and also on the electric field that we apply across the detector. In general, there are two types of interactions. One is called electronic recoils. This is due to charged particles like electrons and photons also scattering off of the electron shell surrounding the xenon atoms. The other type of interaction is called nuclear recoils. These are a result of neutral particles, such as neutrons, and potentially dark matter particles, such as WIMPs, scattering off of the xenon nucleus itself. In general, these two types of particles create different proportions of light and charge in the detector.
We use xenon for our detector, and you can ask, rightfully so, why xenon? What's special about xenon? Well, first of all, you don't have to use xenon. Some of my colleagues use liquid argon or liquid neon. Some use germanium crystals, sodium iodine crystals. Some use scheelite crystals, that's calcium tungstate. So you can use all kinds of different detector media, which is really a good thing because we don't really know what dark matter is. So you want to try with different technologies whether you can find out. But xenon has some very nice features that really help. For a start, the flash of light you get out of xenon is really very bright. That's why xenon is used for car lights, because it's so really intense. So that allows us to go down to very low energies and we can still see the light signal, the flash of light. Also, xenon is a very dense material. What that means is that all the radioactivity that is coming from the outside, the radioactive backgrounds that are coming from the outside and want to, disturb us in our search for dark matter, they get stuck in the outermost few millimeters, a centimeter at most. So by selecting xenon, we guarantee that the innermost volume is really very radio pure.
Of course, there is a little drawback in xenon. It's very expensive, and the cost, it fluctuates a lot. Presently, it's about a few $1,000s per kilogram, so it's very expensive if you think about 1 ton of several tons of material. And so a large fraction of the capital cost of the experiment goes in fact into the target, into these several tons of xenon which we need.
We are inside the steel tank of the XENON 1 ton experiment, which will be filled with a lot of ultra-high pure water to shield the XENON 1 ton detector, which will be filled itself with 3.2 tons of liquid xenon. And so what we see today, and this is a milestone, today we have installed one of the major components of the experiment, which is the cryogenic pipe, which will feed, if you like, the liquid xenon to the detector to be suspended or supported by this pipe. What you see is a very simple pipe or naked pipe, but it's actually quite complicated. This is a vacuum, it's a 400 millimeter diameter tube, which is vacuum insulated with the super insulation with a lot of mylar wrapped inside the inner pipe. And so you can imagine, you will see that inside this 400 millimeter pipe, we have a 250 millimeter tube, all stainless steel, electro-polished, extremely clean, which is actually carrying both inside a separate pipe of 100 millimeter, more than 7 kilometers of cables, which will carry the signals and the high voltage from the detector to the outside wall, to the electronics readout for the experiment. But also the bloodline, which for me is really the liquefied xenon that we will produce in the cryogenic rooms on the top floor of our building. We will take the xenon and make it liquid, and then we run the liquid down this pipe to fill the detector. And the reason why you see it so far away, and this is the principle that we have tested with XENON 100, we want to have this detector extremely low radioactivity, so we cannot put our refrigerator right on top of the cryostat. So we are moving all the cryogenic equipment outside, and since we want 4.5 or so meter of water buffer for shielding the experiment with water, that's the reason of the water tank, we are forced to have this umbilical cord to carry all the stuff, all the signals, and to bring the liquid in and out from the detector to the outside wall. So it's, to me, the image which comes to mind is the detector is my baby, is a baby in the womb of a mother, inside is water, and this is the umbilical, the nutrients, the important stuff which is needed for the baby to function is carried through this pipe.
What we added here, what we changed in this system compared to previous detectors, so like I said, we want to do very long uninterrupted runs of data taking with the experiment, right? We would like the detector to run uninterrupted for, let's say, 2 years, 3 years. That means that if we have any failures, we want the system to continue working even if a failure occurred. So one way to solve this and to increase this resilience is to add redundant pieces of equipment, right? So for example, I was talking about the temperature sensors that are measuring the temperature of the cold finger and are part of the control loop to maintain the temperature of the cold finger and thus the temperature of the xenon stable. So we have 2 sensors, but we are really only using one for the control. If for some reason one of the sensors stops working, we can automatically switch to the second sensor.
The design of the cryostat actually must answer to different requirements. The first one must be mechanical stability and capable to contain and to support the weight of the liquid we are going to put inside, that is almost 3 tons and even more. Actually, the cryostat was designed with a capability to host in a second phase of the experiments a larger volume up to 7 tons. This means that this design is already prepared for the second phase of the Xenon 1 ton, what we call Xenon N ton, where we want to increase the mass and so also the sensitivity of the experiments. And in this design, this capability is already included.
The water tank is, as you can guess by its name, is full with water. It's a huge stainless steel tank, 10 meters, about 10 meters in diameter and 10 meters in height, in cylindrical shape. And inside the cryostat holding the liquid xenon sits, and we use the water as a shield. So the inside of the detector, the cryostat itself will be very quiet and very clean. On top of that, the inner walls of the water tank are covered with PMTs, the so-called muon veto, that will detect particles that arrive to the water. And we use this as a veto.
Since 2013, we started the installation of the system. We first cladded the reflective film foil on the roof of the water tank. Then we had to wait the complete construction of the water tank and also of the substructure and some other elements of the detector.
Then the muon veto group began the installation of the system. Firstly, with the cladding of reflecting foil on the lateral surface of the water tank. Then the PMT was put into place. During the planning phase of the experiment, it is fundamental to calculate the behavior of the structure and equipment.
I'm the coordinator of the Monte Carlo working group. In the Monte Carlo, the main aim is to be able to describe the experiment and the physics inside the experiment well in advance with respect to when the detector is ready to acquire data. Starting from the very large components, then we go down to the tiny parts. The main point is that in this way we have the experiment there and we can choose the best materials, the best shapes, configuration before the construction of the real parts, and so we can see the performances. What we use is, of course, computer simulation. We have some dedicated software. The best one is called Gent4, and so we describe the geometry and also the physics of each particle inside the detector, so we can see what the particles do. So this is in parallel with the screening working group. which defines the level of contamination, of radioactivity of each component. And so we can see what we can afford, what we can stand in terms of radioactivity of any component. Another point in the Monte Carlo simulation is to characterize the response of the detector in terms, for example, of the light collection efficiency. You know that in xenon what we see is light. Particles produce light in our detector. So we must see how smart we are in detect any photons in our detector using the photomultipliers.
Research into the nature of dark matter is of utmost importance to our view of the cosmos. Dark matter must exist in order to turn the tiny fluctuations in the cosmic microwave background into the huge density fluctuations that are observed in the universe today. What is the significance of the XENON project in the world of physics?
XENON is here in the laboratory of Gran Sasso since a long time. We have seen the evolution of XENON from when it was a 1 kilogram experiment to now that is 1 ton experiment. XENON has been the first experiment to use extensively this technology. It has been the leader of the field for a long time. With the previous experiment, the 100 kilograms experiment, it has set the world record for the search of elusive particles of dark matter. Then it started a fierce competition with an American experiment which is called LUX. LUX is a bigger experiment than XENON 100 was. LUX was 300. And so just by the power of the mass it improved on the limit. Now XENON has been reborn into 1 ton version, so this bill will hope. Actually, we hope not only that it will set a better limit than LUX, but that discovers dark matter. That's what we are interested in. So we wish XENON to be the winning experiment in the search of dark matter in the near future. Of course, the long-term future is different.
And I'm here to look at the preparations for XENON 1 ton. We, meaning our particle astrophysics group, has been funding the XENON group for XENON 10, and then XENON 100, and now XENON 1 ton. And it looks like it's really getting together, and I think we hope that they'll be able to start taking data in the fall sometime. We're getting to a very interesting point now where we don't know what dark matter is, and we want to try and find out what dark matter is, and there's a good chance that these people will find it. Well, yeah, I mean, I think if you go look at where XENON 10 was, I mean, it's sort of almost in the corner of a cupboard. And clearly, as you get to be bigger experiments, you need more people to come in and build and operate the experiment. So the big collaboration, it's also good that these are global collaborations now. Many of these projects are now getting to the point where they need not one country, but maybe lots of different countries, and they all bring different expertise to the project. So I think that's good for the students also to meet people from other international communities. That's always part of training the next workforce, next generation workforce.
I think the laboratory is actually a very nice lab to work in. The facilities are really the best in the world, I would say. I know from experience because I've also worked in a lab in Japan and visited some other underground labs. And I think Gran Sasso is by far sort of the most pleasant to work in. So that, and that's of course always an important part because you're going to spend a lot of time underground, and working underground is not always easy. Especially if some other underground laboratories, you have to take elevators down. Here you can of course just drive in, a horizontal access. And also the way it's finished off, and as I mentioned, the facilities. It's really, I think, a very nice lab.
Not far from the high technology of LNGS, you can visit a quiet medieval town of Acergi, where life has never stopped, even after the tragic earthquake of 2009. Many of the researchers love spending their free time in the national park that surrounds the LNGS lab. The park is one of the largest protected areas in Europe, dominated by the Gran Sasso Mountains. The XENON project needs people that take care of the organisation behind the purchase and shipment of materials and machinery, as well as the various appointments and travel arrangements. There is a person at Columbia University who oversees all of this.
I help the technical coordinator, Professor Eleonora with her many tasks at hand. I help with creating the budgets for the proposals and keep the budgets and the expenditures in check throughout the project. I'm also the manager of the schedule and the systems that are going to be delivered to Gran Sasso for the installation have to come in a specific order.
If you have a collaboration of the size of the XENON Collaboration with now 18 institutions and more than 100 people, it's very important that people meet regularly and that people have the chance to discuss that all the subsystems fit into each other. So these meetings are very important, and the collaboration meetings are in particular important also for new members to learn what is going on, for us to see where the other working groups are, and also to see where there are problems, if the schedule is delayed somewhere, if we have to speed up things. It also is a very important occasion for PhD students, for postdocs to gain visibility. Because at the end, this experiment is not done by professors, it's done by many people, PhD students, master students, and they need to have the chance to expose themselves. I'm organizing, together with Elena, of course, I'm organizing most of the meetings. I don't know why, it just happens like that, and I think people don't want to change that. I'm kind of organizing it, trying to make up an agenda, trying to make sure that every subsystem gets the required attention.
Yeah, it's very nice to be at a collaboration meeting and to meet my former postdoc, Ethan Brown, who now has become a professor in the United States very successfully. He came to my group 4.5 years as a just graduated from University of California, Los Angeles, and he did his postdoc and made a nice career in my group.
So my career in XENON started quite young. I started as a young PhD student and at UCLA, and was able to come and spend time at Gran Sasso working on the commissioning of the XENON 100 experiment, and then continue through the process of that experiment with the data taking and the calibrations that we were doing, data analysis. And then from there I went on to do a postdoc at Münster University in Germany, and now I'm working as a professor leading my own group, still continuing to work in the XENON project with XENON 100 data analysis, through the commissioning of XENON 1 ton, and even some developments for future things with XENON N ton and beyond.
It's not only the XENON 1 ton project which allows them to make the career. We have at the same time the running XENON 100 experiment, which is worth up to 1.5 years ago the leading dark matter experiment. Now it's co-leading with the LUX experiment, and that is a very nice opportunity for young people to make a career.
What's inside?
Here are some of the statistics for the XENON 1 ton experiment. A cylindrical water tank, 10 meters in diameter and 10 meters in height, with a total capacity of 700,000 liters of water. 7-kilometer electric cables. 3 tons of liquid xenon. There's a large quantity of material instruments that have to be designed and tested. Let's go back in time to discover who, where, and how.
What you can see is
It's a piece of the Xenon history. It's the first prototype of the Xenon. It's Xenon 10, which in 2006 was shipped from Columbia University to the Gran Sasso National Laboratory, and was operated in 2006 and 2007. And at that time it was the most sensitive dark matter detector.
My main work in this project is to test the photomultiplier tubes that we will use in XENON 1 ton. So the photomultiplier tube is the light detector that will help us search for dark matter. So how this works is that the photons that are produced in the scintillation of liquid xenon are detected in this window. This is a quartz window which allows these photons with low wavelength to be able to pass into the inside of the PMT. They generate an electron in the photocathode, and this electron is multiplied inside the tube, and we read out the signal from these pins, which we afterwards analyze. Now, this PMT is a 3-inch size compared to the 1-inch PMT that we've been using in XENON 100. Since we want to make a bigger detector, we have to cover a larger surface, so we use the 3-inch PMT.
This guy is one of the oldest R&D detectors in Xenon, and with this detector we will soon measure response of liquid xenon to very low energy nuclear recoils. With Xurich 1, with its predecessor, we measured the response to electronic recoils down to very low energies. And this one we optimized for measurements with neutrons. So these measurements are very important for the interpretation of the results from Xenon 100, Xenon 1 ton, or the future detectors, because a little is known about the response of liquid xenon in very low energies where we expect signal.
What we need to find for an experiment like this, where we're concerned about background and we really have to understand our background, we need to find materials that have that are very pure, radio pure. So for this, every material that we put into construction has to be tested. It has to be screened and sourced from particular places so that it's clean. We have a dedicated germanium detector that we do spectroscopy. It's underground in Gran Sasso. So the materials go there, we test them first. If they're okay, then we build them from the same batch of materials. We build the materials from that. And there are several other high purity germanium detectors that we can use underground for this material testing.
I used to study some neutrons out of this neutron generator that we have at the University of Zurich. So as we know, neutrons produce the same type of signal as the beams, which are all dark matter candidates in our xenon target. So that's why we are interested in neutrons. And here we have this neutron facility that produces neutrons for us.
Here we have a 1/16 segment of the XENON 1 ton field cage. Now the field cage is a set of bars which go around the innermost section of the detector to produce the electric fields that we use to extract the electrons and to collect the signal, which are then read out by the photomultiplier tubes. So what is particularly hard about this is to try and get this electric field as uniform as possible. And the way we do this is by building a 3D model of this in the computer and run simulations trying to test different aspects of this design and tweaking it such that we can finally get something that we are happy with. We need to cool it down to the temperatures which it will experience inside XENON 1 ton. We dip this into the liquid nitrogen and leave it until all of it is at the same temperature. We can then remove it and see if there are any deformities. Any deformities would mean that this design is no longer valid and that we would have to go back to the simulations to try and figure out another way of doing it.
In the XENON experiments, so in the project, so as well for XENON 100 and XENON 1 ton, we have our main detector, which is made of Teflon. And Teflon is the material chosen because it has very high reflective power and the xenon detectors are based on light detection. So the more light we have, the better it is for our experiments.
Now we have the distillation column here transferred or sent to LNGS in order to work here and do the distillation. The problem was the transport with a 5-meter version, so we have a small version and a big version, and the big version was too big to get it out of our laboratory, so we had to reduce the height of the distillation column so that we can transport it to LNGS here much easier. And now, as you can see here, the column was lifted up, the small version, and is now upgraded to the full 5-meter version, which will stand on the bottom floor and will go also into the first floor and will have a total length of 5 meters. The total xenon, which are like 3.3 tons, are stored in the restock system, and from the restock system the dirty xenon, which is enriched by the krypton we want to remove, is filled to the distillation column with an input, and then the purified xenon can be taken out at the bottom and is going into the purification system, then to the cryostat, and this filled to the TPC at the end. And the dirty gas, where the krypton is extracted at the very top of the column and is stored in some extra bottle. So we will have about 1% xenon lost in this bottle, but this is, of course, will be stored and is not lost in the end.
In the complex delicate system like xenon, we need to keep under control all the critical parameters, like the pressure or the temperature of the TPC, as well as the pressure and the temperature of the restock, or the velocity of the pump, and etc. So all the subsystem of xenon is on a slow control system, which is composed by hardware, which is the PLC, where we are connected all the device. As also the PLC, we have the touch screen where all the user can control the system, like open and close the valve. At the higher level, we have the SCADA system, which is another system that allows the user to control and monitor the system via web access. If something is wrong, we receive an alarm, and the alarm are sent to all the people, like the shifter, via short message and via email. And once the alarm is received, we take the appropriate action. If it's needed, people go underground to check the detector, or they can even operate via web, because all the shifter have his own tablet with application and can control via SCADA all the parameters of the detector.
Mi occupo di Restox, che è un recipiente criogenico sferico.
I'm in charge of Restox, which is a spherical cryogenic container. It is super isolated and vacuum packed. It is composed of an internal sphere which contains the liquid xenon. It has a capacity of approximately 5 meters cubed and a surface pressure equivalent to 7.3 megapascal. The sphere can contain up to 7 tons of xenon, both in liquid phase at low pressure or in gaseous phase at high pressure. Restox is connected to other systems of the experiment, such as the cryostat, the purification system, as well as the recovery system of the gas in tanks.
È collegato al sistema di recupero di gas in bombole.
The getter is filled with some substance that it's heated up to about 400 centigrade degrees. When the xenon goes through the getter, the impurities in the liquid xenon, that at that point is gaseous, get attached to the particles of the getter, and in that way they are removed from the bulk of the xenon, and we manage to get much more pure xenon. We have a recirculation pump which operates continuously to make the xenon go in the getter and back in the detector. Here in the demonstrator we have one pump and one getter, but in the final detector we plan to operate 2 pumps and 2 getters in parallel, such that we'll be able to duplicate the recirculation speed on top of what we already have.
The gamma spectrometry has the advantage that is the less invasive technique, and of course because we just detect gamma rays from materials or samples or For example, from PMTs, we put inside the measurement cavity an entire PMT, and we can wait for gamma rays. The other advantage is that this facility is sensitive to all the radiation, all the spectrum of the most important radionuclide, which are the uranium chain, the thorium chain, the potassium, which are primordial, but also for radioactive isotopes produced as nuclear wastes, so from human activity, basically.
Another great thing to be working on this experiment is that you meet a lot of people. You meet a lot of people from different cultures, from all over the world, but also from slightly different backgrounds. And you can always ask, you can go around and ask people in the collaboration, why do they work on xenon? If you ask just the people in my group, you get very different answers.
I think in general, physics is quite interesting field, yeah? Because, you know, you have problems, you have to understand them, we have to model mathematically those things, and then go to the lab and test that works. Astrophysics and dark matter in particular is pushing the physics beyond what we know. It's interesting, number one, because it's, as I said, a very difficult problem. So we like difficult things. And then because you do many things. So from the understanding the detector, you have to use all the physics you know, and then to understand how the particles interact in your detector, and then to analyze the data, you use statistics. So it's a field in which you use many tools, and you have to learn a lot. And in particular, in this type of collaborations that only happen when you work in experiments like Xenon, etc., you have the chance to work with very smart and talented people. And even if the people is not physically here in this lab, you always have the chance to learn a lot from all those people. So that's great about working in some group like XENON.
So the XENON 1 ton building, as you see, is made out of glass, and the reason for this construction, which is quite new in the laboratories of Gran Sasso, goes back to the idea to show the world, the visitors, the collaboration, other experiments, when they come into OLB and see XENON 1 ton, to have a chance to see what XENON 1 ton is all about. So if you hide this system inside a standard building, it's never going to be a chance to see the experiment, because the experiment itself, the detector is inside this water tank, which will be closed hopefully for a very long time. But the detector will not work without the systems that you see in this building. So you, by having this vision of, like the Apple stores, the idea to put the XENON 1 ton systems, the key system which makes XENON 1 ton work, namely the cryogenics, all the vacuum system, the data acquisition, the storage vessel, the distillation column, all these beautiful systems that you have seen inside a glass building, or building which is made out of glass walls, was to allow the visitors, the public, and ourselves, our students, our colleagues, to actually appreciate and see how XENON 1 ton works. Because if you enclose it in a box, it's harder for people to understand what we're doing. So, in fact, the idea has been quite successful, because not only it's beautiful, the first motivation is to show the public that we scientists, when we build these experiments, we actually, at least myself, we always connect the science to art. For me, all these pieces are work of art.
XENON 1 ton will have a sensitivity that will allow to discover the dark matter, the existence of this matter, if this matter is have the mass and the cross-section, the capability to interact in the region where we are looking. Anyway, this is an experiment at the border of our knowledge, so even a negative result will be a scientifically important result.
Xenon n-ton depends on what Xenon 1 ton will be able to do. The evolution of these experiments, it doesn't come a priori. It does come from what you measure and what you observe and what are the limits of your measurement, the physical limits of your measurement. I mean, if you have some kind of background, then you have to first think how to eliminate that background. It's not that making a larger experiment solve your problem. However, if it is only matter of having more mass for being able to intercept more dark matter particles, then you will build a larger experiment. So I think that in 1 year time, when Xenon 1 ton will have shown its potentiality and set the new world record, a serious discussion on the next generation of Xenon will be starting and discussed by relevant funding agencies.
Oh yeah, well, I mean, what we've been noticing is that every year or so there's a factor of 10 more sensitivity. Each factor of 10 you get more sensitive, you hope that you're going to see a dark matter signal. Now, whether that happens or not, well, we don't know what nature is, but that's why we're looking. But yeah, the progress from one experiment to the next one to the next one, and you know, this one will be the most sensitive experiment now for 3-4 years, and so it's got a lot of work to do, and hopefully we'll get some very good results from it.
The construction phase was completed at the end of 2015, and in June 2016, XENON 1 ton began collecting data.